Okay guys, so let's look at another example here. Conceptual question. Please try this on your own. So consider these three charges shown here, Q1, Q2 and Q3. Indicate the direction of total force on charge Q2. Okay, if Q1 and Q3 they have the same charge, let's say Q1 equal to Q3 equal to E. Earlier I think I did not mention that there are two basic type of charge, electron. We represent as like E charge with it has charge E, elementary charge E. Proton has positive charge. Electron has a negative charge, so minus E. Proton has a positive charge, so we just write E instead of just positive sign. Okay, proton is E. Note this. Okay, it has a little negative sign here. Electron. Okay. So Q1, Q3 equal to E, meaning these are the positive charges, and then Q2 there given is Q2 is minus E. It means this is the electron negative charge, which is shaded as gray here. These other two are red. Okay. So you want to find what is the net, what is the total force, the direction of F net. Let's call the net force direction at Q2, at location of Q2. Okay, that's number one. Number two, now you, instead of having these two charges, right, Q1 is same, nothing changes, we just swap the Q2 and Q3. Okay, so what happens there? So that's the second part. So this is for number one, this is the case. Okay, so you want to look at this and then you look at this. For number two, you have Q1 is same as Q2 equal to E, but then Q3 is minus E. Okay, so this one I'm going to just leave it here as well, so you guys can see. So see what would be the net direction of the force at this position of Q2. Okay, so please try this out. Okay guys, so wait, let me see my video. Alright, did you guys find this out? So I'm gonna erase this, okay? It's a little messy. Okay, so Coulomb's law, right? So look at this. The first case was what? We have the same type of charges, both Q1 and Q3. Q2 is however different, right? Q2 is negative. So what happens? So how you want to do this is this. At first, look at only one charge at a time, okay? So you have this, I'm going to do this and leave you, explain this and not explain the other one. Q2 is here, it has a negative charge E. Let's look at first what happens with Q1, okay? If we have a Q1 here, and this has a positive charge E, right? So at the location of Q2, what happens, right? What happens, initially we bring this Q2. Now after a minute, let's say you brought this Q1 and you push it here, what happens? Since they have opposite charge, this will try to go towards the Q1, you see? Okay? And then in the third case, we are going to bring another charge that's a little bit further away location, right? Q3, then this has a positive charge. What happens? Now again, we forget this guy, okay? So forget this Q1 now. Now look at only Q2 and Q3. Assume that as though this part does not exist, okay? Now if you bring this here, what happens? Oh, now because this Q2 and Q3, they have opposite charges, Q2 will try to be attracted, try to go towards Q3, okay? So it's going to be like this. Look at this guys here, important thing to see. This arrow here pointing towards Q3 is shorter than this arrow that is towards Q1, okay? So really to make a here also in diagram, right? This arrow is bigger than this arrow, length here we are trying to indicate the total force, right? Shorter arrow, so this is like a longer arrow means more force, shorter arrow means less force. Why? Why do you think that's the case? Look at the distance. The distance between this Q2, this charge and this charge, this is shorter. And we know the Coulomb's force, what? F is 1 over r squared. And these two, the distance between these, two charges, Q2 and Q3, it's longer. So which means the force is going to be smaller. So to say that, okay, this force due to the charge Q3 and Q2 is smaller, we are making that arrow is small, okay? So small arrow, bigger arrow, okay? Same thing, you follow the same thing, and then when you had actually charge Q2 as a positive, then you see something like this here, okay? So that is for the second case. For the second case, right, so you see here, we have this charge here, Q2. If you bring Q1, what happens? It will try to repel, so it will try to go away. But then this Q3, this should be a little bit different here, guys. I'm going to make it. So this should be a little bit, you may not see, this arrow is little longer, okay? The repulsion one is little longer. But then Q3 has the opposite charge, so this Q2 will try to attract, so this is another arrow here, it try to go there, right? So both of the arrows point in the same direction. This arrow is, I'm going to make it here, guys. Maybe you guys are like wondering what I'm trying to do there. Q2, Q3, okay? And this is, both of these are positive E, this has a negative E, right? So because the force experienced by Q2 because of this Q1 is repulsive, they are both going that way, so let's make this big arrow, repulsion. But then the force experienced by Q2 because of this Q3 is attractive, right? They have the opposite charge. So another arrow would be kind of, it's also, this is also attractive, right? So this charge will try to go towards that, okay? So again, the arrow would be something like this. I'm drawing it down here. Guys, something is not right here. Okay. I mean to draw this further away, okay? So see this distance is shorter than this distance here, so draw here. This is negative e, okay? So now that would be better. So you see this arrow is due to this Q3, okay? I'm drawing this too. So if you make a net arrow would be like this, right? You have this one and then you have another, you plus, really you are adding that, and then another one. So that will give us really like a long arrow if we are to do the net, okay? This is the net force, okay? Direction of the net force. Alright. Okay. Okay, so here is a thing to look at. So, Coulomb's law example. So, can we neglect the gravitational force of attraction between two charged particles when considering the electrostatic force? What do you guys think? Do you think we can basically ignore or neglect the gravitational force of attraction between the two charges in comparison to electrostatic force? What do you guys think? So consider two protons, please. So try this out. Let's say mass of proton, m proton, equal to 1.67 into 10 to the power minus 27 kg. Coulomb constant, you guys know already, right? 9 into 10 to the power 9 Newton meter square per Coulomb square. G is gravitational constant, 6.67 into 10 to the power minus 11 Newton meter square per kg square. Okay, and then we are given mass of proton. So what we are trying to say here is, let's say, assume you have a two proton of this mass. Let's say both of these charges E and E, right? If it's a proton, it has a positive charge. So and then they are separated by some distance r, okay? We don't know r, it is not necessary, but please try to see if you can figure this out. Can you neglect the gravitational force of attraction between two charged particles when considering the electrostatic force? Try this out, please. Okay guys, so how far did you guys get here? Did you try? So, what do we think we need to do first? Well, given this charge is proton, it has a mass, it is separated by distance r, it has a charge, positive E, right, elementary charge. If we, to see whether we can neglect gravitational force of attraction or really in this case repulsion, right, if we have both a proton, we have to see, well, we have to see, you know, we cannot talk about gravitational repulsion, guys, so let's make it, yeah, let's make one as a proton, one as a, oh, it doesn't matter, let's do it just as a, this, okay, just numerically, and I'll explain it later on. So let's see, what do we need to do here is we can compare two forces, right? One is force due to gravity, another is force due to electric interaction, right? So we can compare gravitational force and electrostatic force, okay? So let's see. So let me move this guy away. So here, let's do first, write down given information. We are given, okay, just write this down. Given, I'm going to write MP as mass of proton, okay, 1.67 10 to the power minus 27 kg, K as 9 into 10 to the power 9 Newton meter square per Coulomb square. Gravity constant G 6.67 10 to the power minus 11 Newton meter square per kg square. This, and the charge is E is, let's say, not let's say, the charge E means what? This is the elementary charge in proton, 1.6 into 10 to the power minus 19 Coulomb, okay? And the distance r is given. Oh, we are not given information about r, but since we don't really need that information. So let's see the force of gravity, okay? So let's see force of gravity. I'm going to write Fg here, okay? Force due to gravitation. Maybe this may, then you guys may start looking at the mass times gravity. Let's write this F force no, I don't want to write whole word. Let's write F dash as the, you know, gravitational force, okay? Gravitational force. So we can distinguish between, you know, the electrostatic force. Just F dash just for the purpose of this problem here, okay? So we know F dash is given as what? F dash equal to G m1 m2 over r square, right? Newtons, right? Law of gravitation here. So G is what? 6.67 into 10 to the power minus 11 times m1, that's the mass of the proton. m1 and m2, we have the same mass, so we are just going to do 1.67 times 10 to the power minus 27. I'm squaring this because this mass and this mass, they are same, okay? Same mass, so just squaring, right? Squaring 1 times m2, this is both m, okay? So squaring. Divide by r square, alright? So let's call this as one equation. Now if, let's say F is a force due to electrostatic force, easy to say. Oops, not it. Guys, I'm gonna write this one, that's really hard.